All right, let's talk about something pretty incredible. We're going to dive into how a simple, flat piece of aluminum gets turned into something complex, strong, and, well, useful. So, you ever look at something like a sleek laptop case, or maybe a cool piece of modern furniture, even just a simple metal bracket, and wonder, how in the world did they do that? Right? How does a perfectly flat sheet of metal become this complex, three-dimensional part? Well, that's exactly the mystery we're going to unravel today. Okay, so the main goal here is pretty straightforward. We're shaping a metal sheet, and the whole journey really kicks off with two key ideas: forming and bending. First up, let's zoom out and look at the big picture. That's forming. Think of this as the main category for, well, for everything we're doing. It's the whole process of changing the shape of metal. And here's the key part: you're not adding or taking away any material. Nope. You're just reshaping what's already there. And tucked under that big umbrella of forming is the star of our show today: bending. Now, this is a specific type of forming. It's where we take a straight piece of metal and literally force it to curve. This is the magic that creates all those cool angles and shapes we see all around us every single day. But before we can bend anything, what are we even starting with? Usually, it's either a sheet or a plate. And you know what? The difference is actually super simple. It's all about thickness. A sheet is anything under 6 millimeters thick. And a plate? That's its bigger, beefier cousin, anything over 6 millimeters. And knowing the difference is a huge deal, because it tells you just how much muscle you're going to need for the bend. Of course, we're not just bending flat stuff. We also bend hollow things, right? Like a tube and a pipe. Now, they might look almost the same, but they have totally different day jobs. A tube is usually for structure, like a bicycle frame or a chair leg. But a pipe, that's all about transport. It's designed to move stuff like water, gas, or other fluids from point A to point B. Okay, so we've got our material picked out. Now for the fun part. How do we actually make the bend? This brings us to the tools and the forces. These are the real players that make the magic happen. So the main tools for this transformation are these three heavy hitters. You've got the press, which applies this massive but super controlled pressure to stamp a shape. Then there's the roller, which uses these big rotating cylinders to create those nice, smooth, gradual curves. And finally, the punch. You can think of it like a precision chisel, pushing right into the metal to create a really specific, sharp angle. And all of those tools, they really only have one job: to apply force. It's a simple idea, right? A push or a pull. But in our story, that force is the spark. It's the action that kicks this whole transformation into gear. So we've used our tools to apply this big external force. But what's actually happening inside the aluminum, like down at the microscopic level? Now we get to the real science of the bend. And trust me, this is where things get really fascinating. So when that force hits, the metal doesn't just, roll over and give up. No way. It actually fights back. And that internal resistance, that pushback from inside the material itself, that's called stress. It's basically the metal's reaction to being pushed around. Now, if our external force is stronger than the metal's internal stress, well, something's got to give. And that give is what we call strain. So strain is the actual physical change in shape you can see. It's the bend itself. It's the proof that the battle between force and stress has been won. Okay, so we've made a bend. But how do we describe it so everyone's on the same page? We use two key measurements. First is the angle, which is pretty much what it sounds like: the degree of the corner, like a 90-degree angle. Then there's the radius. This one's a little more specific. It measures how tight the curve is on the inside of the bend. So a tiny radius means a super sharp corner, while a big radius gives you a nice, gentle sweep. All right, now let's introduce the first major villain in this whole story. Picture this. You bend the metal to a perfect 90-degree angle. You remove the force and... wait, what? It moves back a little, maybe to 92 degrees. That annoying little habit is called springback. It's like the material has a memory and it's trying its best to go back to being flat. It is a constant headache you have to predict and overcome. And springback? That's just one of the things that can go sideways. So let's dive right into the conflict of our story. What happens when bending goes wrong? These are the challenges that fabricators deal with all the time. So here's a quick breakdown of what causes the most common problems. If you apply way too much stress, way too fast, you're going to get a crack. If you use the wrong kind of force or don't support the metal properly, you might see a wrinkle, like an unwanted fold. And, like we just talked about, that darn material memory is what leads to springback. So, we've got these potential bad guys, cracks, wrinkles, and springback. How do we beat them? Well, this brings us to the final act of our journey, perfecting the final form. This is all about the clever techniques used to get that shape exactly right. The solution, boiled down to one single, powerful word, is correction. This is the umbrella term for all the little tweaks and fixes you do to beat those errors, compensate for things like springback, and just dial in that absolutely perfect final part. Now, correction isn't just one magic button you press. It's a whole process. It starts with the setup, double-checking all your tools and settings before you even start. Then comes adjustment, which is all about making small, smart changes to the force or the tools to get the result you're aiming for. And finally, there's straightening. That's the hands-on part, where you manually or mechanically fix any little warps or bends that weren't supposed to be there. So we've walked through the forces, the science, the challenges, and all the precise corrections needed to make that perfect shape. But you know what? A perfect part means absolutely nothing if the process isn't safe. In the middle of all this heavy machinery and incredible force, the single most important component is the guard, the safety system that protects the person running the machine. Because at the end of the day, the ultimate goal isn't just a perfect bend in a piece of metal. It's making sure the person who creates it can go home safely every single time. That is the real measure of a perfect process.